we've discussed a few things about logarithms. We talked about how they're the inverse of exponentials, and we've done transformations with them. But now it's time to talk individually about some properties of logarithms themselves. Now, some of these properties are going to sound a tad bit familiar, but also unfamiliar completely. That's because logarithms are still new to us, but the properties we're going to use are tied really closely to some properties that we do know about. We have three properties in this first little box of logarithms. They're ways to expand and condense logarithms. So that's the words you're going to be seeing, expand and condense. The first one says it's the product property, and it says that if you are multiplying two things inside of a logarithm, okay, inside of the argument of a logarithm, then you can expand that logarithm in the following way. You could rewrite this as logarithm with a base b of the first thing that's multiplied plus the logarithm with the same base of the second thing that's multiplied. Notice that the logarithm, log, and the base did not change. All I have done is separated it or expanded it into two logarithms with an addition sign. So again, to expand, we are going to add the logs. To condense, we are going to multiply the values, because these equations can go in either direction. If it says expand, that means you're writing all of the logarithms. If it says condense, you're writing all of it as one logarithm. The second property we have today is called the quotient property. Quotient has to do with division. And it's kind of like the opposite. So if with multiplication we added, what do you think we're going to do with division? Subtract. That's exactly right. So we have logarithm base b of m, the first thing. We're going to subtract the logarithm with the base b of the second thing, of the denominator. So again, if we are dividing, it's really like subtracting. So to expand, we subtract the logarithms. To condense, we divide the values into one argument. The third property is called the power property. It has to do with when we see that we have a logarithm with something in the argument, which is in the parentheses, and that something in the parentheses has an exponent. All we have to do for this is take the exponent and drop it in front of the log for logarithm, so it'll end up looking like n times the logarithm same base b of m. It becomes a big number in front. Yeah, it becomes a coefficient. So to expand, the exponent moves to the front. To condense, the number in the front becomes the exponent for that term. Now, something I want to point out to you here is these rules, the reason I said they might look familiar is because they are actually our exponent rules. Y'all remember mad spam? Mad spam said if we multiply, we add. Guess what we're still doing with logarithms? Multiply means add. Adding means multiplying. Our quotient rule for exponents said divide, subtract. Well, guess what? That's still the same for logarithms. If we're dividing an argument, we can subtract the logarithms. And last but not least, we have power to a power means multiply. If you have a power in a logarithm, you multiply it in front. So it's still our mad spam rules, just applied to logarithms instead of applied to exponents, which is nice because we didn't actually learn anything new. We've just applied it to something new. Those are the properties of logarithms, to expand or contract. And those are going to be the words you see, expand and condense. Of course, we can ask you all sorts of questions when it comes to using these properties of logarithms, including these 4 examples here. It says, evaluate the following 4 things using the logarithmic properties given. So these 2 things right here are going to be what we use to answer all of the questions below it. What 2 numbers did they give us the value of the logarithm for? They gave us for the value for 3 and the value for 7. And that's going to be all we know right now. Basically, what they've done is they've used a calculator in a way I haven't taught you yet, and they got these values. You're not going to have to use the calculator to do the logarithms. We're just going to use the values that they gave us here. Okay, so my question for you is, if I ask you to find log base 2 of 3 divided by 7, is there a way you could rewrite this, maybe in an expanded form, so that you can use the values you know? That answer would be yes. We know that division means subtraction. So what I'm going to do is I'm going to rewrite this as log base 2 of 3. Good morning. Thank you. Log base 2 of 3 minus log base 2 of 7. I'm allowed to do that because my division rule or my quotient property says if I'm dividing an argument, which is the parentheses stuff, I can just expand it and do it as 2 separate logarithms as long as I subtract those. Well, now we have values for each of these things. Log base 2 of 3 is 1.585. I know this because like literally it's in that little cloud section. I'm going to subtract the logarithm, base 2 of 7, which is the other value in the cloud, 2.807. Now, a little bonus question. Does anyone know why I made this equal sign squiggly? Does anybody know what that means? Precisely. Equal but not equal is what she says. We use the phrase approximately equal. This has to do when we are rounding. So we're rounding these numbers. If we look in a calculator later, we're going to get a string of decimals that we'd have to round. Once you round, technically in math, your equal sign should become a squiggly equal sign because we're rounding. But you know what? Those are numbers we can type in our calculator. So we go there, home screen, we type 1.585 minus 2.807. We press enter. And you get another approximation of negative 1.222. That is the value of log base 2 of 3/7. We found this by using the properties of logarithms to estimate the answer instead of having to do a logarithm change of base formula, which I will teach you about later. Does that sort of make sense how I did that? What if we look at the second example? It says to find the log base 2 of 21. Is there a way I can make 21 out of the number 3 and 7? 7 times 3, right? So we're saying that this is actually 7 times 3 or 3 times 7. Okay, if I am multiplying two numbers inside an argument of a logarithm, how can I expand that? Multiplication becomes what? An adding. So great, I can expand this and I can write this as log base 2 of 3 plus log base 2 of 7. I can add them because 21 is 3 times 7, so I can just expand those logarithms. Now again, we're just substituting in the values from the little cloud section. Log base 2 of 3 is 1.585, and I'm going to be adding that to 2.807 this time. Oh, I messed up. What should I have made my equal sign?
The squiggly.
Yeah, the squiggly one, because it's an approximation. We know that those are rounded numbers. So again, whenever we actually add these numbers, beep, 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 type it in your calculator, 1.585 plus 2.807, it is 4.392. I trust you're able to type things in a calculator's home screen. Moving right along, the next two use a new rule. They use that last rule that we had on our paper. How do I know they use that last rule? What do you see inside the argument there? An exponent. Where can we put the exponent to simplify this? In the front, yeah. So we're going to actually rewrite this as 2 times the logarithm of base 2 of 7. I said that backwards. Log base 2 of 7. Okay, if you look at the little cloud, don't we have a value for log base 2 of 7? Yeah, so we can just multiply 2 times 2.807, which I got from the little cloud section, and we can get our answer. Beep, 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 we type it in the calculator, we would get 5.614. Does that make sense? Let's make sure it makes sense. This last example is for you. I want you to figure out what log base 2 of 3 to the 6th power is, using properties of logarithms and the given. Okay, if we were doing this one, what property did you use to be able to deal with that number 6 up there, the little floaty 6? Yeah, it goes to the front. It's called the power property. So we would actually rewrite this as 6 times the log base 2 of 3. But again, we have a value of log base 2 of 3 from the given, from the little cloud part, which is 1.585. And I would hope that you just did that quick little multiplication problem and you got approximately 9.51. How'd we do? So that's using the properties of logarithms when you have values for the logarithms. So some of your homework problems are going to be like this, where we give you the numbers to use. And sometimes, like the next problems on the inside of this little packet, are going to just give you letters that you are just going to expand and condense without giving me like an answer, without giving me an approximate answer. We're just going to work on expanding and condensing them. But it just uses properties from the front of this paper. I do kind of want to expand some of these properties, just kind of make it in a way that's maybe helpful for you. If you know that a number is in the numerator, which means top of the fraction, it's going to be a plus. And this doesn't make sense yet, but I promise it will in a second. If a number is in the denominator, that is going to be a minus because it is divided. And remember again that an exponent just goes to the front and vice versa. So those three things are just another way to talk about those properties from the front. That multiply means add, divide means subtract, power to a power means multiply. Essentially, numerators are positive, denominators are negative, and powers go from the front to the top. So we're first going to work on expanding natural logarithm of 5x to the 7th over y. Cool. Every single part of this gets its own logarithm. The 5 gets its own logarithm, the x to the 7th gets its own logarithm, and this y gets its own logarithm. Do you see that 5 and x to the 7th are in the numerator? Do you see that y is in the denominator? That's going to tell me the sign, positive or negative, for those parts, for those logarithms. So we would start by expanding this to natural log of 5. It's positive because it's in the top. I'm going to add the natural logarithm of x to the 7th. It's positive because it's in the top. But when I write natural logarithm of y, should it be positive or negative? Negative because it's in the denominator. Do you see how every single term gets its own logarithm? Now there's one more thing I can do to clean this up. Can anybody think of what I can do to expand this a little further? Hint, it has something to do with this. Bring the 7 to the front. Yeah, the very last thing we're going to do when we're expanding is move all of the exponents to the front. So my actual answer here should be natural log of 5 plus 7 natural log of x minus natural log of y. Looks weird that that's a helpful thing to be able to do, but we do need to be able to expand and condense logarithms in this way. So I like to move all of the things to their own logarithm first. Positives are on top, negatives are on bottom, and then move all of the exponents. That's my personal preference. So if we look at the second one, just based on what we see in the argument, are there going to be any negative logarithms here? No, because there's no denominator. Great, but every single part gets its own logarithm, which means the 3 gets its own logarithm and the x to the 4th gets its own logarithm. This would look like this. We'd say log base 6 of 3 plus log base 6 of x to the 4th. Couple things to point out on this question. Did I change anything about the log or the base? But notice I had to write the base on this one. We didn't do that in the problem right above this because it was base e, so we got to use the shortcut of natural log. But when a base is showing, show the base every time. One more step to finish cleaning this up. What is it? Bring the 4 to the front. Yeah, we need to move this 4 all the way up there to the front, which means this would be log base 6 of 3 plus 4 log base 6 of x. Fabulous. Let's make sure we got it, and it is a bit of a challenge, but I'm going to have you guys do this third one. I want you to expand log base 2 of x to the 4th divided by 4x to the 5th. There's a chance you're going to do it wrong, and that's okay, so maybe do it in pencil, and we will fix it. But we got to start trying them on our own. So go ahead and try it by yourself. I'll give you a few minutes. All right, let's see where we're at, because we're either lost or we think we have it. When I start this one, I would notice that there's x to the 4th in the top and then 4 y to the 5th in the bottom. So I have two things in the bottom that need two separate logarithms, meaning this will start to expand to log base 2 of x to the 4th. That's positive because it's in the top. But then I have two things that are negative. So this is going to be minus log base 2 of 4 and minus log base 2 of y to the 5th. There were two things in the denominator, so there are two terms that are negative. Do we see that? Even if we didn't get it right when we did it, do we see that? Of course, with this one, there is still one more step that I need to do to clear this up. I've got two exponents here. Both of them need to go to the front of their respective logarithms. So this 4 is going to float up to the front of the first logarithm, and this 5 is going to float to the front of the second logarithm. Third logarithm. LOL. That means this would be 4 log base 2 of x minus log base 2 of 4. No change to that one because it didn't change. Minus 5 log base 2 of y. Yes? Fabulous. Okay, that's expanding. But what if it already starts expanded and we want to condense it? This time, and these problems go really, really quick, we are trying to get them to be written as one logarithm. But remember, positive goes in the numerator, negative goes in the denominator, numbers in front go to the exponent. So the first thing we're going to do on this problem is we're going to rewrite this with the exponents showing. Meaning, when I'm condensing, I look for big numbers in front, like this number 3. None of the other logarithms here have a big number in front of them, so I'm good. That 3 is going to float up to the top of, or to the exponent of its argument. So I can rewrite this problem as log of 9 plus log of x to the 3rd minus log of y. Now, a good question I kind of expect you to ask is, Ms. Quigley, all of these problems have parentheses and then you're not writing parentheses. You're right. The parentheses are optional up to a certain point. So when there are more than one thing inside your logarithm, if there's just a single number or a single letter, technically it makes sense that you don't need the parentheses. But the moment it gets complicated, you try to add or subtract, you have 3x, you have more than one thing, I want you to put the parentheses. Oh no, we're not done yet. That's just step 1. Because now I have a plus and I have a minus that I need to take care of. Now, question, what is the sign of this first one? I don't see a plus or a minus in front of it, so what do we know about it? Is it positive or is it negative? Positive. So I'm going to go ahead and write the plus just because we're learning. Because my rule that I'm telling you is every time there's a plus, it goes in the numerator. Every time there's a minus, it goes in the denominator. So if we go to write this as one logarithm, notice I'm going to put a lot of complicated stuff in here, so I go ahead and put my parentheses. What two things should I have on top of this logarithm?
9 and x to the 3rd.
Very good. What should I have in the bottom? Y. That's it. Now we're done because we have it condensed to one logarithm. The moment you write log just one time, you're done. Extra bonus question. I was not writing a base on this one. Why? Now, what base is there when it just says log with no number? 10. This is called a common logarithm, so we know the base is 10. We just don't have to show it because it's super common. In problem number 5, the first thing I said to do was look for numbers in front that you can make exponents. Are there any numbers in front? No, so are there going to be any exponents? No, all I have to do now is condense it to one logarithm. If I write the logarithm of and then leave like a space there for the argument, I know that the first term is positive and that second term is negative. So what should go on top? What should go on bottom? X over 9 is correct. These are just the rules or the properties of logarithms applied to expanding and condensing. Not really. Okay, number 6 is for you up at the top of the next page. I want you to practice condensing. Remember, first thing you do is look for big numbers in front so that you can make those exponents. I'll give you a minute to try this one. First thing we look for is big numbers in front of logarithms, LOGs. I see that there's a 6 here and a 3 here. Yes, I know that before today you would have said, Miss Quigley, you would have called that a negative 6. I know, but for properties of logarithms, we're just trying to take the number, not the sign, with it. Because we don't want to make that power negative 6. That's weird. It would cause a whole lot of mess to the math that you don't want to deal with. So we just take the 6. And we move those up here, beep, 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 so that our next line of this problem should say log base 2 of 7 minus log base 2 of x to the 6th plus log base 2 of y to the 3rd. After this, all that's left is to deal with the signs in front of all 3 logarithms. I know that this one is positive, and this one is positive, but then this middle term is negative. The order doesn't really matter. That's why I like to go with the terms. The terms that are positive go in the numerator, the terms that are negative go in the denominator. Which means this log with a base of 2, when I condense it, should be 7 y to the 3rd power over x to the 6th power. How'd we do? Okay, so one more tool that's super duper helpful when it comes to logarithms is called the change of base formula. Now we noticed a while back that if we tried to type a logarithm into the calculator, there were only 2 types of logarithms we could type in. Those 2 types of logarithms are common logarithms and natural logarithms. They have a whole button on the calculator. The problem is, not all of our logarithms are going to be common logarithms or are going to be natural logarithms. So mathematicians were like, we need to figure out a pattern, we need to figure out a way to be able to evaluate these logarithms quicker. So they discovered this change of base formula. I don't know how many of the boxes are out near you, but I would do this next part with 2 highlighter colors. I think it would be helpful if you can find 2 colors to write in. In the change of base formula, the way you can type in any logarithm to a calculator, log base b of a, is to type in a common logarithm or a natural logarithm that looks like this. Logarithm of a divided by logarithm of b equal to, or is the same as, natural logarithm of a over natural logarithm of b. Basically, I prefer to use this one. So if you want to be like me, this is the one I prefer to use. It is a formula for us to be able to type in logarithms with a different base than 10 or e. This is the only way our calculators can evaluate these logarithms. This is also going to be how the people who wrote your notes got the numbers from the front. When they gave you log base 2 of 3 and log base 2 of 7 from the front of your notes, this is how they figured this out. So to see this being used, we're going to use the change of base formula to evaluate the following, rounding to the nearest thousands. Now all I need to do is remember what is the base and what is the number I'm taking the logarithm of. so that they go in the right places. But to evaluate log base 3 of 8, I'm actually going to do common log of 8 divided by common log of 3. Now, those two things are buttons I can press in my calculator. So to do the change of base, we're going to make the fancy fraction. We're going to put log of 8 on top and log of 3 on bottom. So let's do that. Everybody grab their calculator with me. How do we make the fancy fraction? Oh, that was the actual question I want a response to. How do we make the fancy fraction? Yeah, alpha y equals and the number 1. That's going to make the fancy fraction. Where's the log button? Under the x squared. Very good. So we just press log and then put 8, close parentheses. Then we scroll to the bottom, and then we press the same buttons. Log 3, close parentheses. When we press enter, it's going to give you a string of decimals. These are not usually going to come out to cute numbers, so we have to round. Notice I put the little squiggly parentheses because we're going to round this number. Parentheses, what is that called? Thousandths. So that saves 3 decimals. So if I look, and I'm going to write this down so y'all can see what I'm talking about. I get this number. I want to save 3 decimals. So I look at the 4th decimal, and that's where I do the little rhyme. 5 or more, raise the score. 4 or less, let it rest. So I should actually round this number to 1.89, what? 2 or 3? 3. So this answer will be approximately 1.893. Again, use the squiggly equal sign because it's an approximation. I had to round. And it's literally that simple, but you have to remember this formula because this is the only way we type logarithms in our calculator besides natural log and base E and common logarithms. Okay, make sure we got this. 6 is yours. Go ahead and use the change of base formula to figure out what log base 6 of 24 is. When you do this, we should be calculating in our calculator. Log of 24 divided by log of 6. When we do that the same way we just did the one before it, using the fancy fraction, making sure we close our parentheses, we should get 1.774. Thing that's going to get you on these problems is I'm going to be particular about rounding. You must round correctly to get these right. So make sure you understand how to round. And if you don't, figure it out. Ask for help, Google it.
What did you say?
Make sure you round correctly is also basically what I'm saying. Okay, those are properties of logarithms. That's really what it's going to be for today.